Welcome back, 7th grade team. This is Mrs. Allen, the math coach at Bouchon Middle School. It is School Spirit Week, so I am sporting my Eagles t-shirt, hashtag Eagle Excellence. And again, I'm glad you're here to join me as we continue week 2 of our probability series. Our weekly learning target is to be able to investigate and describe the difference between the theoretical probability and experimental probability of an event. The supplies you will need for today's lesson are your standard notebook and your pencil to take notes, your calculator, and of course, your I can attitude. Let's begin by taking a look at our independent practice from yesterday. So for question number 1, we have an experiment that Dana performed using a spinner. And the question asks, which of the following statements, if true, if Dana conducts the experiment another 500 times? So again, Dana's going to conduct the experiment further, and we want to know which of the following statements are true. And what's important about this is we know that if she's conducting an experiment several more times, that the law of large numbers tells us that the experimental probability is going to approach the theoretical probability. So we first start by calculating the theoretical probability of Dana landing on yellow. It's a 4-color spinner, so the theoretical probability of yellow would be 1 yellow out of 4 total possible outcomes, which is 25 hundredths, which is the same as 25%. So the more times that Dana conducts the experiment, the more the experimental probability will approach the theoretical probability of 25%. Therefore, she will land on yellow less than 40% of the time. For number 2, we have a simulation with a standard coin, and the question is which table shows an experimental probability of landing on tails that is closest to the theoretical probability. Again, we need to calculate the theoretical probability to be able to compare the value of the experimental probability. We know the theoretical probability of landing on a tail is 1 out of 2 because there is 1 tail on a coin out of 2 possible outcomes, which is 5/10 or 50%. And for our experimental probability, we simply need to go through our options and calculate the the experimental probabilities of landing on the tails. And we see our options here on the left-hand side. For example, with letter A, we know that there are 18 12s in this particular trial out of the total number of trials, which would be 27 plus 18. So your answer would be C, because 48% is closer to the theoretical probability of landing on a tail, which is 50%. And then in number 3, we have Joe, who claims that the probability of getting ahead when flipping a coin is 1/2, and Ashley flips it 10 times, and her probability is 3/10. So what's important about this question is for you to understand and be able to explain that the probabilities are different because one is based on theoretical probability and one is based on experimental. So go ahead and pause the video. I want you to compare this answer key with your independent work, make any adjustments necessary, and annotate your notes as possible. When you're finished, resume the video and we'll continue. Today's learning objective is to describe changes in experimental probability as the number of trials increase. So we are doing a continuation of our learning objective from yesterday. Today's vocabulary terms are theoretical probability, trials, and law of large numbers. It is important that we're continuously exposed to this theory, the law of large numbers, which means that the more times we repeat an experiment, the closer the experimental probability will come to the theoretical probability. Let's visit with Bianca from Cyberchase for real. She wants to see a movie, but she's having difficulty deciding which movie to watch. She decides to flip a coin to decide, but the coin keeps landing on heads. She becomes curious about when does 50-50 actually become 50-50? Let's take a look.
Stay right where you are. It's Cyberchase for real.
just in time. I really don't like it when I miss the start of the movie. There were 2 films I really wanted to see. One is this new dinosaur movie, and the other stars Giovanni, my favorite actor. So when I got to the box office, I don't know which one to pick. I'll flip a coin. Heads, dinosaurs, tails, Giovanni. Heads. I wonder what'll happen if I try that again. Heads. Again? Heads. It doesn't seem fair. Poor Giovanni didn't come up once. Is this fair? Even Steven? 50-50? Finally. But that's 3 heads to 1 tail. Doesn't seem fair. So I decided I wanted to do some research on why Giovanni didn't win half the time. Fred's Encyclopedia of Probability. Let's see. 1 in a million, 1 in 1,000, 1 in 100. Here we go, 50-50. When flipping a fair coin, about half the time it will be heads and about half the time tails. See note, see note. Note, this will only happen if you flip the coin many times. Well, I flipped the coin 4 times, but I got 3 heads to 1 tails, and that's not half and half. You have to flip a lot more than 4 times. Hey, do you remember I asked you to hold my place? Yes. Okay, great. Thanks. Wait a minute! Flipping 10 coins 1 time is the same as flipping 1 coin 10 times. Excuse me. I'm trying to find out if I flip a coin a lot of times, will the results really be 50-50? Heads about half the time and tails about half. Will you help me? Come on, it'll only take a minute. How many heads? Raise your hands. Only 3 heads and 7 tails. With 10 coin flips, that's still not very close to 50-50. I need to try this with a lot more people. This better work. Can I borrow that for a second?
Sure.
Thank you. Hello? I need everyone to flip a coin to see if heads really does come up about half the time. Just the people who got heads, raise your hands. How many people here?
350 paid at the gate.
Wow, then it is true. I think I could say that's pretty much 50-50. Thanks. Fred's encyclopedia was right. If you flip a coin just a few times, it might not be close to 50-50. But if you flip lots of times, like 350, then it will be closer to heads about half the time and tails about half.
Similar to our activities from yesterday, Bianca was able to discover the law of large numbers. We are now going to explore the law of large numbers through another activity where we will graph our results. Creating our graph is a great way to tie into next week's RPS at home lessons with Ms. Bradford, who is going to be working with you on graphing representations. You see, there's so many connections in math. So let's look at our graphs that students are using to predict what will happen when you flip a coin 30 times. Student number 1, the red line, predicts the more trials completed, the higher the percentage of heads. This looks very similar to when you did slope with Miss Whitaker last week, the idea of a constant change. Now, student number 2 predicts that an increase in the number of trials completed will also result in an increase in the percent of heads. Student number 3 predicts an increase in the trials completed will be an increase and reduction in the percent of times the coin lands on heads, but the percent heads is approaching the middle, which would represent 50%. And last but not least, the last student, the green graph, predicts that as the trials increase, the percent of heads will increase and then remain constant. What are your thoughts? Do you have an idea of what type of graph would represent if we flip the coin 30 or more times? If so, briefly draw your thoughts and then resume the video. After you write your prediction, we will conduct a game of chances with a virtual coin maker with heads and tails and graph our results to see if our graph looks similar to any of these predictions or to see if my graph looks similar to yours. This graph shows the final results from our coin toss. Each person's graph would look different, but one thing is for certain. If we were to conduct this experiment 1,000 or more times, we would notice the points on the graph would maintain near the red line, which represents 50%, similar to our probability line. So let's go ahead and try a problem together, and then you can go ahead and try one on your own. So for this problem, we want to write our answer in the box. The answer will be a percent. That's important. The answer will be a percent. Okay. So we have a classic mixed box that contains 54 bags of assorted snacks. Here's some key information here. That's why we have these bullets. So first thing we need to know is all the snacks in the bag are the same size and shape. That's important because that means they each have equal probability of being selected. Next, there are 8 bags of Lay's potato chips, 4 bags of sour cream and onion chips, 4 bags of barbecue chips, 12 bags of Cheetos, 12 bags of nacho cheese Doritos, 7 bags of Cool Ranch Doritos, and 7 bags of Fritos. I'm going directly for the Cool Ranch and the regular Doritos first. What about you? So you randomly select 1 bag of snacks from the bag, record the flavor, and place the snack back into the box. So this is with replacement because you're putting it back. This process was completed 10 times. The experimental probability of selecting a bag of Cool Ranch Doritos was approximately 23%. This process will be completed 1,000 more times. The experimental probability of selecting a bag of Cool Ranch Doritos will get closer to what number? And again, this would be as a percent. So this is important. The experimental probability of selecting a bag of Cool Ranch Doritos will get closer to. Now this sounds to me like we're talking about the law of large numbers because we're talking about completing this experiment 1,000 more times. We're specifically looking at the Cool Ranch Doritos. The Cool Ranch Doritos, that's what our focus is. And it says the experimental probability of selecting a bag of Cool Ranch Doritos is currently 23%. That's the experimental probability. So it means that what we need to find now is what is the theoretical probability of selecting the Cool Ranch Doritos. The theoretical probability of selecting the Cool Ranch Doritos. Cool Ranch. Okay. Cool Ranch. So how many Cool Ranch Doritos do we have in the bag? It tells us there are 7, rather that's a box. 7 bags of Cool Ranch Doritos. So 7 favorable outcomes out of how many total possible outcomes? Well, it tells us here in our word problem, there are 54 bags of assorted snacks. Certainly I could look at the image on the box right here, but I also want to make sure that I look at the word problem first because sometimes these figures could be different. So you want to make sure that you have the accurate figure from the word problem. So 7 out of 54 is our ratio of Cool Ranch Doritos to total possible outcomes in the bag. And this is approximately 13/100ths. 7 out of 54 is approximately 13/100ths. But if we remember in our problem, it actually gave us specific directions because it said we need to express it as a percentage. So we take that 13/100ths and we multiply it by 100, which gives us our percent of 13%. So the experimental probability will get closer to 13%. Why? Because 13% represents the value of the theoretical probability of selecting Cool Ranch Doritos out of our box. Now I want you to practice with shoe problems. Pause the video, complete the problems on the slide. When you are finished, resume the video. Okay, so for our practice problem, number 1 says we have a table that shows the result of tossing a coin 25 times. And the result gives us heads or tails. And the question is, what is the experimental probability as a percentage of the coin landing on a tail? And so what we had to do was highlight the number of tails. And how many did you have on your paper? 16, that is correct. Because we highlighted the number of tails, you might have circled it, and then you actually counted the number of tails. So the experimental probability of a tail would be 16, which is your favorable outcomes, out of your total number of trials, which was 25 trials. And 16 divided by 25 gives us 64/100ths. And the question is asking us to convert it into a percent. And so 64/100ths times 100 gives us 64%. Number 2, circle a box to choose the correct answer that we want to select. Did you highlight or did you underline or did you circle true? I hope so, because that's very important, because sometimes it might say not true, sometimes we might be asked for what is false, but in this case, it wants to know which of the following are true. We also want to make sure that it's not more than 1. In this case, it is only 1. We go through the first one, that experimental probability and theoretical probability will always be the same. That is false. They will not always be the same. And I put an F at the right to indicate that. The second one, for a small number of trials, the experimental probability will be greater than theoretical probability. Again, that's not always the case. That's false as well. The third one, for a large number of trials, the experimental probability will be greater than the theoretical probability. Again, not always, so that one would be false as well, because the words are very important. And then last but not least, as the number of trials increase, the experimental probability will usually get closer to the experimental probability. Was that the one that you had as true? That is correct. And that again is our law of large numbers. How did you do? So again, our learning objective for today was to describe changes in experimental probability as the number of trials increase. After today's lesson, you again were able to learn and apply the law of large numbers that tells us the more times we repeat an experiment, the closer the experimental probability will come to the theoretical probability. Now it is time to reinforce the content learned in today's lesson. So for your independent work time, be sure to complete week 8, day 2 in your learning plan. Show all of your work and annotate. Once you're finished, strengthen your math skills by completing 2 Dreambox lessons. So let's take a look at our future connections. Today's learning objective was to describe changes in the experimental probability as the number of trials increase. Tomorrow, we will compare the theoretical probability and experimental probability of the same event. Remember to share your avatar with me and your other classmates on our learning Padlet. Feel free to upload a second avatar. And also remember that we have a Padlet where you can upload your probability experiment to share with the team as well. Both links are found on your learning plan. We'd love to hear from you. And I thank you for being my learning partner today. Be safe. See you tomorrow. And remember, make today so awesome that yesterday gets jealous. Bye-bye.